Lesson 4.8 is going to be about horizontal and vertical shifts of your sine, cosine, and tangent functions. Now, it would seem like the translation of the figures or the functions would be easier than the scaling of them, but we looked at scaling in Lesson 4.7 and we saw that we could change the amplitude or the period by doing multiplying numbers, and there's the A and the B values from the scale change of x comma y with ax by. So we looked at that in Lesson 4.7. But now in Lesson 4.8, we're actually going to work backwards and we're going to look at the translation. What would happen if you add on something, some amount h, and then you have your y plus k amount. So remember, this is going to be the horizontal translation, and this k is going to be the vertical translation. And I think sometimes these are harder for, especially when you're starting out for you guys, because when we move things left and right and up and down, we don't change the appearance of the graph that much, but sometimes we can move them to strange amounts for the zeros, what the zeros are, or the intercepts, and then it's hard to track where they've gone. So we always have to match up something that we know, and sometimes we don't know if it's a sine function or a cosine function because they're so closely related to one another. The tangents, we'll know those when we see them. So I think the best thing to do would be just to dig right in and see if we can't figure out what's going on. We're going to call phase shift. It's going to be the least positive or the greatest negative magnitude of a horizontal translation. So this horizontal translation that we did before, this h, in trigonometry, the trig functions, we're going to call it phase shift. Okay? It's going to be represented by the variable h. So the phase shift will be the variable h. We've seen that variable before when we worked with regular graphs that we were translating left and right. The vertical shift is the amount that the graph has been moved up or down from its center, so that's going to be our k amount. It's represented by the variable k. It's going to just be called vertical shift. Okay, so it wants us to consider the function p of x is equal to the sine of x plus 2/3 pi. So it's identified the phase shift. Well, if we go back to, let's say we had the parent graph y equals x squared, which was a parabola, and I said, what's happening if I say y equals x minus 2 quasi squared? Well, you would tell me that because this is inside the grouping symbol, a minus 2 would shift this 2 units to the right. Remember that back from chapter 3? Well, the same is true in the trigonometric functions. This is the argument of my function, and it says I'm going to do a plus 2/3 pi. So inside the grouping symbol, remember it's doing the opposite of what you think. This would actually move this 2/3 of a pi to the left. 2/3 of a pi to the left. So we're going to say the phase shift for this is negative 2/3 pi. You could write it that way, or you could write it as minus 2 pi over 3. All right, so this is going to be the same rules as when we were working with just regular those parent functions on the pink note card. Okay, now it wants us to consider the function f, where f of x is equal to the sine of x. Find the image g under the translation. So this would be like if we had a big capital T right here. Nothing is happening because it's on the x, because it just says x. So no horizontal translation. Okay, but we have a y plus 2, so we're going to move it up 2 vertically. Okay, because remember, the rule is the rule, and the rule tells you exactly what you're going to do. Then it wants us to sketch that graph. First of all, it says find the amplitude and the period. Now this would go back to what we were doing before when we had y back in less than 4/7 equals the sine of x. Okay, so this is y divided by 1 and sine x divided by 1. So in this case our a is 1 and our b is 1 also, isn't it? Remember, amplitude is the absolute value of b. Absolute value of b would just give us 1. Alright, period of the graph. Period of the graph is 2 pi times the absolute value of a. A is 1 in this case, so the period of this graph would be 2 pi. So we're not going to shrink it or stretch it, we just want to move it up to vertically. Okay, so when we think about that, think about y equals the sine of x. It's not doing anything horizontally, and outside the grouping symbol we put a +2 because we want to move it up 2. Now a good way to do this, remember, is if you find your maxes and your mins and your zeros. Alright, well let's look at the minimum values and the maximum values, and we'll look at the old values and the new values for this. Okay, so on our parent function, we had a minimum of -1 and we had a maximum of +1. So remember, on the old sine function it would go up to 1 and down to -1. We're going to bump those up 2. So that means our new minimum is going to be, add 2 on, would be 1, and our new maximum will be 3. And so then you can go back to your yellow note card, and you can look on your yellow note card at your parent function of sine. You might want to grab that so you can look at it. And we're going to move the points up 2. Okay, so we had a 0 at 0, 0, and we're going to move that. I'm going to go by tick marks of 1 here. I'm going to move that up 2. Alright, we had a maximum at 1/2 pi, and that was at 1. Well, now that's going to be at 3, isn't it? We had a minimum at, we had a 0 at pi, and so now that's going to be up to 2. We had a minimum at 3/2 pi, so that's going to get moved up to 1. And at 2 pi we're back to 0, so that's going to be at 2. Okay, over here on the other side at -pi/2, that's where our minimum is, so it's gotten moved up 2 to +1. At -pi we have a 0, so that's going to get moved up 2 until we're at 2. At -3/2 pi we're going to have our maximum, so now we're going to be up to 3, and at -2 pi we're going to be back to 2. So then we can draw our little curve connecting all these dots like so. Okay, so that's just our graph of sine that's been moved up 2. Okay, the next question says true or false. Oh, by the way, no, I don't have that graph. Number 3 says, the graph of any circular function and its image under a translation are congruent. So it's asking you, does the graph stay congruent? In other words, if you moved it back by sliding it left and right, or up or down, would it map back onto itself exactly? Would it be? It wouldn't be a shrink. It wouldn't be a shorter period. It wouldn't be stretched, larger amplitude or smaller amplitude. And the answer to that should be true. It'll be congruent. They'll just be moved left and right and up and down, just like the parabolas and the cubics and the absolute value graphs and so on that we learned about on the pink note card. We're back in chapter 3. Okay, number 4, it says, consider the function y equals the cosine of x plus pi/3. Identify the phase shift. So once again, this is inside the grouping symbol, so think about that for a minute. Instead of moving it 1/3 of a pi to the right, it's actually going to move it 1/3 of a pi to the left. So the phase shift is minus pi/3. Remember, it's the opposite from in the grouping symbol to the equation. It says, can you sketch 2 sketches or 2 cycles of this curve? Okay, well, it's our cosine function, and it got moved 1/3 of a pi to the left. So what we want to do is we want to figure out where the new zeros would be, and where the new minimum numbers would be, and where the new maximum numbers would be. Okay, so you grab your note card and you look on the yellow note card where the zeros of the cosine function are. The zeros of the cosine function, one of them was at a half pi. Alright, so we have to take the 1/2 pi and we have to subtract pi over 3. So a half pi minus pi over 3, 1/2 minus 1/3 gives you 1/6. So it's going to be at 1/6 pi. So I'll have to make that really close here because that represents a half pi. I'm going to make it right here at 1/2 pi, or 1/6 pi. Okay? We have another one at another 0 on that function at 3/2 pi. So if we take 3/2 pi and we subtract 1/3 pi, 3/2 minus 1/3 in terms of pi would give us, well, let's see, 3/2 minus 1/3. So we're going to hit math enter. We make that go to 7/6 pi. Okay, so 7/6 pi. 6/6 is 1 pi, so it's just past that at 7/6 pi. All right. If you wanted to find another one on your graph, you would go to negative 1/2 pi, so negative 1/2 pi, and then we're going to subtract 1/3 from that. Okay, we're going to get math enter. We'd be at negative 5/6 pi. Okay, so negative 5/6 pi would just be on this side of, because that would be negative 6/6 pi. Okay, if you wanted to subtract another 1/3 pi from that, we could. Now you'd be at negative 7/6 pi. Does that do that? I don't think that would be at negative 7/6 pi. What did I say we were at? We were at negative 5/6. Negative 5/6. And we want to subtract 1/3 of a pi. It says negative 7/6. I think that's kind of odd. Because I'm thinking you'd want to go to the left another, not a negative 1/3. You want to go to the left from there another increment of pi. So if you're at negative 5/6 and you wanted to go 1 pi to the left, you'd wind up at negative 11/6. Yeah, that makes more sense. Okay. In other words, these zeros are going to be spaced 1 pi apart because they occur every half period. Okay, then in between those, where we're going to find our maximum and our minimums, aren't we? In between those. So we did have, if I wrote minimum here, okay, we did have a minimum at negative pi, didn't we? Negative 1 pi. And now we're going to go 1/3 of a pi to the left of that. So that would be minus 1/3 pi would be at negative 4/3 pi, wouldn't it? Okay, so if I'm thinking of this in terms of thirds, negative 4/3 pi, let's see where that would be. It would be halfway in between here, wouldn't it? And at negative 4/3 pi, we'd be at our minimum, which is going to be negative 1. I'll just put negative 1 on this third tick mark going down. Put positive 1 there. So we'll be halfway in between here. We'll be at negative 1. Halfway in between here, we'll be at positive 1. Halfway in between here, we'll be at negative 1. And halfway in between here and the next stopover, which would just be past 2 pi, we'd be back here to positive 1. Alright, so we're going to draw that on there. And it looks like so. Okay, so that's our cosine graph being moved 1/3 of a pi to the left. Number 5 says, under the translation, so this is the rule that they're giving us here, x plus 3/4 pi y minus 3. The rule is going to shift the graph 3/4 pi to the right and then down 3 units, right? Is it going to change the amplitude? And the answer is no. So the amplitude of the graph will stay on 1. Is it going to change the period of the graph? No. Then the period is going to stay 2 pi, isn't it? Okay? And then it says the phase shift. The phase shift is this. It's going to go 3/4 of pi to the right. I'm going to write that as 3 pi over 4. I want to find the equation of the image of this, of a sine function. A sine function. So, we're going to do sine. Inside our parentheses, if we want to go 3/4 of a pi to the right, we're going to write that as x minus 3 pi over 4. Because that would take you to the right inside the grouping symbol. And then down 3, we write a minus 3 on the back end. Okay, that one was pretty easy, wasn't it? Let's try number 6. We're going to look at this picture, and we're going to figure out what equation this is. Now, this is a little bit trickier because you first have to figure out if you're doing a sine function or a cosine function. You'll know that based on the points that they give you. All right? This goes from negative 2/3 pi over to 4/3 pi. Those are the marked amounts. And if I trace that, that is one whole period of your graph, isn't it? So the period of this graph is equal to 2 pi. So that's the first thing we're going to check. Okay? Now, we need to figure out how far this thing has been translated, either to the left or to the right. Remember on your sine function on your parent graph, you want this point. You want to find this point. It's halfway between your minimum and your maximum when the function is increasing. So it would be this 0 right here in the middle of that period that we'd want to find. Okay? And so if I'm going from negative 2/3 pi to positive 4/3 pi and I'm doing a period of 2 pi, I just want to go 1 pi behind it or 1 pi in front of these other zeros here. So if I took that 4/3 pi and subtracted off 1 pi, which would be 3/3 pi, I would be at 1/3 pi. So that 0 right there is at 1/3 pi over and 0 up. Okay? That's what its coordinates are. So we just basically want to move this graph, this sine function, 1/3 pi to the right. So inside the grouping symbol, we're going to have x minus pi over 3. That's going to move it to the right. We're not moving the function up or down, are we? Now, when we get to number 7, we are moving the graph up or down. So here's what we need to do. We need to look and see what the period of the graph is. So here are the points that they have marked for us. And the distance goes from negative pi to positive pi, so the period of this graph is 2 pi. On the way up, between this minimum and this maximum, this is where our 0 is. So this is that point that we like to locate on this particular function, and it's 0, 2. So the period didn't change, so that means we're not going to stretch it or shrink it horizontally, but we are going to bump it up. And it used to go through 0, 0. That point is now 0, 2. So this is the graph of the sine function moved 2 units upward. All right, so we're going to say it's y equals sine x plus 2. Notice we're not doing any grouping symbols. If you felt like you needed one, you just put them around the sine x right here. Because the plus 2 needs to be on the back end all by itself. Okay, let's try something a lot different now. Let's go to the next page and do the tangent function. Number 8 says the graph below represents the translation image of y equals the tangent of x. And it's a translation image, so it's been moved left or right, up or down. Okay, so find an equation for this function right here. Okay, we're going to notice that these are the asymptotes and they're not on with dashed lines. They were given in solid lines. So we'll change those to dashed lines to think of them as not really part of the function, but something that you could use to count the width of the period. All right, does that make sense to you? So you have one of these going through 1/4 pi, and the next one over here is going through 5/4 pi. So that would give you a total distance right here of 4/4 pi or 1 pi. So 1 pi is the period of this function. So again, it's not been stretched or shrunk horizontally. Okay, We just need to know where the points of inflection are. The points of inflection appear to be right here. Okay? And so now we're going to say that this function has been moved. Okay, we have to figure out how far it's been moved. All right, we know that from our yellow note card, the vertical asymptotes, let me get a different color here, are supposed to be at the odd multiples of pi over 2, aren't they? So we're supposed to have one at pi over 2, which in terms of fourths would be 2/4 pi, right? So we have it at 1/4 pi. It should be right here at 2/4 pi, which tells me that this graph got moved 1/4 of a pi to the left, didn't it? That moved 1/4 pi to the left. So that's what happened to it. You can tell that from the 0 right here. That point of inflection should be at 0, 0 if you were looking at the parent graph, and that's been moved 1/4 of a unit to the left. Okay, so to write the equation of that, we're going to say it's the tangent. We're going to put parentheses there because we'll fill in the argument for going left or right. So this is going to be x plus 1/4 pi, or you could have pi over 4 as well. Okay, that was kind of a good one. Kind of get your feet wet on tangent here. Number 8 is also a tangent graph. It says the graph below represents the translation image of y equals the tangent of x. Find the equation for the function. Well, are the asymptotes where they're supposed to be on the parent graph? And the answer to that question is, on the old graph, the asymptotes are at 1/2 pi, aren't they? They should be right here on the old graph. And now they're on the pi amount. So you could say this is either pi over 2 to the left or pi over 2 to the right, depending on how you're thinking about it. Because the asymptotes are off by 1/2 pi, aren't they? All right? So you could have an answer, and you could say y is equal to the tangent of, and let's say you thought it was going to the left. If you thought it was going to the left, then you'd have x plus pi over 2, wouldn't you? Somebody else might think, oh, they moved that graph to the right, and they may put x minus pi over 2. So you would both be correct. Because the period of this function is only pi, 1/2 pi to the left is equivalent to 1/2 a pi to the right. Okay, now notice the points of inflection, though. They're now up here, aren't they? They'll each have a y-coordinate of 1, which means the graph got moved up 1. Which also means that we can just attack a 1 on the back end. So we would have either or on this. Either or. Okay, I'm going to let you take some time to do the matching on 9, 10, and 11 because I think you've figured out now enough of whether it's going to the left or to the right or to on the up or the down. They're all sine functions, so you can compare them all to the original parent function on your yellow note card. So pause the video and do those 3 on your own. All right, number 13 says consider the function defined by y equals cosine of x minus pi plus 1 using the window negative 2 pi to 2 pi and negative 3 to 3. Graph the function on your graphing calculator and sketch it below. All right, so let's put that graph on our graphing calculator. All right, so we've got the cosine of x minus pi minus or plus 1. Okay, let's put my window set on. Negative 2 pi to 2 pi, that'll work. The problem is I need a little more room at the top and the bottom, don't I? So it says go negative 3 to 3. So here's our graph. All right, it looks like 2 mountains, doesn't it? All right, so we've got a 0 at 0. Alright, looks like we have another 0 out here at 2 pi. We have a 0 at negative 2 pi. Alright, and what's it doing halfway in between? Well, at negative pi, it's at its maximum. The maximum of this used to be negative 1 to 1, but now we're adding 1 to it. The minimum is 0, and the maximum is 2. Okay, so we're going to have it peaking out halfway between. Alright, I think we would be able to get the minimum point here, or the other maximum point. Is that what yours looks like? Okay, exactly what did it ask us to do? It says use this window, so we're kind of restricted to this window, so we're just going to stop it at those 2 points. And then we're also going to find all the places where it's at its maximum value. That was at negative pi and at pi. Okay, it would wind up being k times pi, where k equals an odd integer, if you're going to write the whole pattern out. Okay, hopefully that's what you got when you did it. Alright, sketch 2 cycles of the sine of x plus pi plus 2 on the interval from negative 2 pi to 2 pi, and label all the x and y intercepts. Alright, well, a little bit of a chore for us, because we're going to move the graph pi to the left, because a plus pi means we go pi to the left, and 2 upward. Pi to the left and 2 upward. So again, you have to take a look at where the maximums were and where the minimums were, and then you're going to move them. Okay, so we did have, on your parent graph of sine, we had a 0 at 0. And now that 0 is getting moved pi to the left. Okay, pi to the left. But then it's also getting moved up 2. Right? So at negative pi, I'll just go by tick marks of 1 here. Negative pi, it's now at 2. Okay? Then if I go another pi, the next 0 is at negative pi, right? And at negative pi, it would get moved to negative 2 pi, and it's going to get moved up too. All right? At pi, there was a 0, so that one got moved to the left. It would now be at 0. Let's move that up too. At 2 pi, it would get moved to pi. That would be there. 3 pi would get moved to 2 pi. So those are all going to give us values of 2. Okay? And then halfway in between, it's going to be doing its maximum and its minimum, isn't it? Okay. So here, we'll go all the way up to 3. Here, we'll go down to 1. Back here, we'll be up at 3. In between here, we'll be at 1. So I don't know if I can get this curved on here or not. Oops. Maybe go down a little lower there. That's what it would look like from negative 2 pi to 2 pi, wouldn't it? It's kind of hard to do on that little graph paper. I should probably give you better graph paper. Okay. There are more of these problems that I want to do with you. 15 is a tangent problem, and then 16 is a real-life problem about a harbor and a tidal wave. What's happening in a 24-period occurrence of a tidal wave, and then 17 and 18 are some more where we're going to look at some scale factor in there. So I want you to stop right now on these, and then we're going to do those right away in class when we get to class, and then we'll check those few that I asked you to do back on 10, 11, and 12, and then you can get started on your assignment. These are a little bit more tedious than the ones we're doing with scale change, though.